Settle in and let your breathing slow the way the night air slows everything down. Outside, the sky looks wider than it did earlier, not because it changed, but because you finally got quiet enough to notice. Astronomy is mostly this: long stretches of waiting and small, patient moments when the universe answers back in a whisper. Tonight, with the Sleepless Scientist keeping you company, you will follow one of those whispers all the way to something that does not want to be seen. A black hole does not shine, it does not pose, it does not cooperate. So you learn to watch the light around it, the bent glow, the missing center, the calm evidence of gravity doing its work. And very slowly, across the whole planet, humans learn to build one gentle eye out of many. You are standing under a sky that looks empty, and you are already mistaken. It is not empty. It is crowded with messages that take their time. Every point of light is a delayed announcement from far away. And astronomy, at its most honest, is the practice of letting those delays be enough. You do not grab the universe. You do not chase it down an alley. You wait, and you measure, and you try not to lie to yourself. If you are lucky, you catch a whisper that survived the whole trip. And if you are very lucky, you catch a whisper that went near a black hole and came back slightly shaken. You start where astronomers always start, with the simplest kind of noticing. Light arrives, and you decide to take it seriously. Not because it is dramatic, because it is all you get. Light is a messenger that cannot bring the original object with it. It cannot deliver a star to your doorstep, so it brings a receipt instead. A thin, tired receipt, stamped with information about color and brightness and timing. You learn that color is not just beauty. Color is a clue, a temperature report, a chemical hint. A star that looks blue is not feeling artistic. It is burning so hard that the word hot stops being useful. A star that looks red is cooler or older or both, like a coal that has learned patience. And even when your eyes cannot see the details, your instruments can. They can spread light out into a spectrum, like a quiet fan of rainbow. In that spread, dark lines appear, little missing slices. Those gaps are atoms and molecules, stealing specific colors, like picky thieves. Hydrogen takes what it likes, sodium takes what it likes. And from those tiny thefts, you can name what a star is made of from across ridiculous distance. This is the kind of power that sounds like magic, until you remember the cost. The cost is time and calibration and the humility of knowing you might be wrong, because the universe is not trying to be understood. It is simply happening. So you build tools that are honest about how little you can hold at once. A telescope, in spirit, is a bucket for light that would otherwise miss you completely. You do not make the light brighter out there. You just collect more of it here. A wider mirror, a larger dish, a better chance of catching something faint. And faint is the normal setting of the cosmos. Most things are far. Most things are dim. Most of the important drama happens behind curtains of dust. So you become fond of a different kind of light. Not the sharp little wavelengths your eyes evolve to enjoy, but longer waves, slower waves, the ones that feel almost lazy. Radio light, it is not calmer because it is kinder. It is calmer because it is longer. and longer waves do not get bullied as easily. Dust that blocks visible light will often let radio waves pass through. Gas clouds that look like solid darkness in a telescope can become transparent if you listen at the right wavelength. So you trade the crispness of an optical picture for the steady honesty of radio. You stop trying to see the universe like a tourist. You start trying to hear it like a patient neighbor through a wall, and you realize something that is both comforting and unsettling. Most of the universe cannot be touched and will never be visited. So astronomy becomes the art of careful listening from a great, safe distance. Safe, mostly. Because even here, under your calm sky, the planet is spinning fast enough to make you dizzy if you ever truly felt it. You are riding a turning world, and the stars look still only because your senses are easily bribed. Telescopes, however, are not so easily fooled. They must account for the turning, the wobbling, the atmosphere that shimmers like heat above asphalt. They must fight the air itself, which blurs starlight into a soft, trembling smear. So, astronomers put telescopes on mountains where the air is thinner and less eager to interfere. They build domes that open like sleepy eyelids. They sit in control rooms with dim screens and cold coffee, and they wait for the sky to behave, which it does, only when it feels like it. If that sounds like an odd way to do science, it is. But it is also the only way to do astronomy, because you cannot put a star in a lab. You cannot ask a galaxy to repeat itself for the camera. You take what the sky gives and you try to make your question small enough to fit inside the answer. Speaking of answers that are too big to hold comfortably, you eventually wander toward black holes. Not because you want to, because the math will not stop pointing at them. A black hole begins as an idea that feels impolite. Gravity, taken seriously, does not promise you a gentle ending. Gravity is not a force with feelings. It is geometry with no mercy. Mass tells space how to curve, and curved space tells mass how to move. That is the calm sentence version. The practical version is this. If enough mass ends up in a small enough place, the path outward becomes too steep. Light tries to climb and fails. Information tries to leave and cannot. And you get a region where escape stops being a thing. People call it a cosmic vacuum cleaner because people love the comfort of a wrong metaphor. A black hole is not a roaming mouth hunting planets. From far away, it pulls the same way any object of the same mass would pull. If the sun became a black hole, the Earth would still orbit at the same distance with the same boring loyalty. You would freeze, of course, but that is a separate problem. The black hole part only becomes special when you get close. Too close. Close enough that leaving requires more speed than light is allowed to have. That border has a name that sounds like a place in a story. The event horizon. It is not a wall you hit. It is not a glowing fence. It is a one-way edge in the map. Cross it, and every path you can take points inward. Not because someone forces you, because space and time are shaped that way there. And the strangest part is how ordinary it looks from your side. If you could hover just outside and your nerves did not revolt, it would not look like a trap. It would look like darkness, shaped like a missing piece. Your story, however, would become private. No light you shine could report your condition back out. No signal could return. Congratulations, you have become a secret. That is the core horror of a black hole. And it is a quiet horror. It does not scream. It simply refuses to share. So how did humans, who are trapped on one damp planet, ever suspect these things exist? They began, as usual, by noticing what looked wrong. A star would orbit something invisible, too heavy to ignore. Gas would whirl and heat up as if falling toward a center that did not glow. X-rays would flare from a region of sky that looked empty in visible light. And you start to understand that invisible does not mean absent. It can mean dense and quiet and very serious about keeping its light to itself. In the 1960s and 1970s, astronomers found compact objects in binary systems. A visible star would circle and wobble and show signs of being tugged by a partner. But the partner did not shine. It did not show a surface. It did not pulse like a neutron star. It was just mass hiding in darkness, and the visible star could not stop confessing its presence through motion. Motion is an honest witness. A star cannot fake a wobble. So black holes moved from rumor to likely. Then, in the centers of galaxies, another clue kept showing up. Huge jets of matter, spearing outward for distances that make the word huge feel inadequate. These jets shine in radio and other wavelengths, and they come from tiny central regions. A small engine making a galaxy-sized effect. You do not get that kind of power from a polite campfire. You get it from gravity, doing what gravity does best, turning falling into heat and motion. And at the heart of that engine, the math keeps placing a black hole, not as decoration, as the only thing dense enough to organize that much chaos. It helps at this point to remember something calming. Black holes are real, and they are not your problem tonight. They are far. Space is mostly empty. Even in a galaxy, the average distance between stars is so large it feels like a joke. The nearest star system is years away, even at the speed of your impatience. So the black hole in the center of the Milky Way is not lurking around the corner. It is about the distance of a long, slow dream across the whole galactic disk. And yet, despite distance, humans wanted to see one, not just infer it, not just trust the equations and the indirect clues. They wanted an image, something your brain could hold, like a proof. But black holes do not shine. So you do the next best thing. You look for the glow of everything falling toward them. Matter does not usually fall straight in. It has some sideways motion, some angular momentum, a fancy phrase for stubborn spinning. So it spirals. It forms a disk, an accretion disk, which is a calm name for violent friction. Particles rub past each other. Magnetic fields twist. Temperatures rise to the point where atoms come apart, and electrons wander freely. The disk becomes plasma, the fourth state of matter, which is what you get when heat stops being polite. This disk can glow brighter than the galaxy around it in some wavelengths. Not because it is large, but because it is efficient at turning gravity into light. The closer the gas gets, the faster it orbits. The faster it orbits, the hotter it gets. And right before the event horizon, the disk can be bright enough to outline the darkness inside. That is where the idea of a shadow comes from. Not a shadow cast by a light source behind the black hole, like a hand puppet, but a shadow created by the black hole stealing the paths light could have taken. Photons that wander too near can be captured. Others can be bent into curves, looping around, taking scenic routes that feel like cheating. So instead of a simple dark circle, you get a dark region surrounded by a ring, a bright loop of lensed light, like a halo made of hot panic. It is not a portrait in the usual sense. It is a silhouette made from warped space, and to see that silhouette, you need a target whose shadow is big enough to notice from here. Most black holes are too small, too far, too shy. Even a supermassive black hole, millions of times the sun, sits at distances that reduce it to a speck. So, astronomers made a strange shopping list. They wanted a black hole that was both very massive and relatively close. Mass makes the shadow larger. Closeness makes it larger still in the sky. But those two qualities rarely come together in a neat package. There are two famous candidates. One is in a distant galaxy called Messier 87, usually shortened to M87. It sits in the Virgo cluster, far enough away that the numbers feel abstract. But its black hole is enormous, billions of suns packed into a region smaller than your sense of fairness. M87 also has a jet, a bright, famous jet, blasting outward for thousands of light years. That jet is like a signpost that says, something heavy is working here. The other candidate is closer, much closer, in the center of your own Milky Way. Sagittarius A star, a name that sounds friendly until you learn what it is. That one is smaller than M87, but it is so near, astronomically speaking, that its shadow could still be large enough to chase. In the end, the first successful image would come from M87 because it holds still better. It is a patient monster. Sagittarius A star is more restless, like a flame that will not pose. But before any imaging happens, there is a problem so basic it feels embarrassing. No single telescope on Earth has enough resolution to see a black hole shadow. Resolution is the ability to separate details, to distinguish two close points as 2 points, not one blur. It depends on the size of your telescope and the wavelength you observe. Shorter wavelengths give better resolution. Bigger telescopes give better resolution. And if you want to see something as small as a black hole shadow, you would need a telescope dish about the size of Earth, which sounds like a funding request designed to end a conversation. So, astronomers did what they usually do when reality refuses to cooperate. They used a trick. They made many telescopes act like one, not by connecting them with steel, but by connecting them with time. This is where the story gets quietly beautiful in a tired human way. Instead of building one impossible instrument, you coordinate existing observatories across the planet. High in Hawaii, in the deserts of the Americas, on mountains in Europe, even at the South Pole, where the cold is so intense it feels personal. Each site is a lonely outpost, watching the same target at the same time. They collect radio waves at a wavelength small enough to sharpen the view, around 1 millimeter, a realm that sits between radio and infrared. And they record the incoming signal with extreme precision. This technique is called very long baseline interferometry. It is a mouthful, so people shorten it, and the meaning stays the same. You spread out your antennas. You create a baseline, the distance between them. The longer the baseline, the sharper the combined resolution. In effect, you synthesize an Earth-sized telescope using Earth itself as the framework, but only if you can keep time. Time is the fragile thread holding this together, because to combine signals from distant telescopes, you must know exactly when each wave crest arrived. Not roughly, not within a second, not within a blink, within a fraction of a microsecond, and even that feels like bragging. So each observatory uses an atomic clock, often a hydrogen maser, which is a device that keeps time with a steadiness that borders on obsessive. These clocks tick with the regularity of physics itself. They do not care about weather or feelings or the night shift getting tired. They just tick, and with those ticks, the recordings can later be aligned, like matching the same melody captured by microphones around a stadium. It is still hard. The atmosphere introduces delays because water vapor and air density slow radio waves slightly. Each telescope has its own quirks, its own noise, its own small lies. So calibration becomes a kind of ritual. So you treat every telescope like a stubborn instrument that needs to be persuaded into honesty. You measure its gain, meaning how loudly it claims the sky is speaking. You measure its phase, meaning how it shifts the rhythm of the incoming wave. You measure its noise, the self-made static of warm electronics pretending to be cosmos. And because you are doing this at a wavelength where water vapor is a petty tyrant, you measure the air too. You point at bright, simple sources, calibration beacons, and you ask the same question repeatedly. Are you hearing the sky or just yourself? Most nights, the answer is a little of both. So you subtract and correct and subtract again until you are left with something that seems stubbornly external. You think the hard part is staring at the black hole? Wrong. The hard part is proving that your equipment did not hallucinate it. When the Event Horizon Telescope observes, you are not a person with a camera. You are a nervous system spread across continents. You are an ear pressed to a wall in Chile and another ear pressed to the same wall in Hawaii. You are listening for the same faint syllable at the same time while the Earth rotates underneath you. That rotation is not a nuisance. It is part of the trick. As the planet turns, the distances and angles between telescopes change. The baseline stretches and swivels, sampling different slices of the target structure. You let the Earth drag your instruments through a slow dance. And in that dance, you collect pieces of information that no single telescope could ever earn alone. In interferometry, you do not record a picture. You record relationships. You record how similar the signals are between two sites with a delay and a phase shift. It is like trying to reconstruct a song by comparing how it echoes between two distant alleyways. You never hear the full orchestra in one place. You infer the orchestra from the way the sound lines up. This is why the final image will always feel a little haunted. It is not painted directly by light onto a sensor like an old-fashioned photograph. It is assembled cautiously from agreements between faraway listeners. So on observing nights, you become obsessed with weather in a way that feels unfair. Not the gentle weather outside your window. The high-altitude water vapor kind of weather that decides whether a millimeter wave even arrives intact. At some sites, the sky is crystal clear and still useless. At others, thin, invisible moisture makes the signal wobble, like trying to read a street sign through rising heat. You wait anyway, because waiting is what astronomers do when they cannot negotiate with physics. When the window opens, it is brief. A few nights in a year, a few hours in a night, when enough of the planet has good conditions at once. This is why the whole effort feels like an international heist planned around clouds. One missed flight of weather, one storm in the wrong hemisphere, and the planet-sized eye blinks. Now imagine you are inside one of those observatories, not as a glamorous scientist, just as a tired human in layered clothing. You are in a control room lit by monitors that never learned how to be dim. Outside, the dish points with slow certainty, motors humming like a refrigerator in the next room. There is a checklist, of course. There is always a checklist. Pointing, model, focus, receiver temperature, clock status, data recorder status, and then you stare at numbers that represent the sky arriving. You cannot see the black hole. You see a stream of voltages and time tags. You see a plot that twitches. You see a correlation coefficient that rises a little. And someone exhales as if that matters. It does matter, unfortunately. Because if you lose coherence, you lose the ability to stitch the planet together later. So, you keep the rhythm. You let the hydrogen maser tick in the background, quiet and smug. You keep the local oscillators stable so your frequencies do not drift. You monitor the system equivalent flux density, which is a fancy way of asking how deaf you are tonight. You swap between the target and calibrators, like touching base with reality. And you do it again and again, because this is not the kind of experiment where you get a second try next week with the same setup. The Earth will be in a different position. The atmosphere will be in a different mood. And the source itself, the glowing mess around the black hole, may shift like a restless animal. For M87, that restlessness is slow enough to tolerate. For Sagittarius A star, it is faster, more impatient, and it will punish you later. But for now, you are chasing M87, a galaxy so far away that your mind tries to turn it into a symbol instead of a place. So let it become a place again. You are looking toward the Virgo cluster, into a region crowded with galaxies, like lanterns in fog. M87 is an elliptical galaxy, smooth and swollen, not much spiral prettiness. It has a core that is overfed. It has a jet that looks like someone punched a hole in reality and left the bruise glowing. That jet has been known for more than a century, a thin line in early photographs. Long before anyone said the words Event Horizon Telescope, people knew something in that core was extravagant. The jet is not made of solid stuff like a fire hose. It is plasma and fields and particles accelerated to ridiculous energies. It shines in radio and optical and X-ray and even gamma ray. It is collimated, meaning it stays narrow over insane distance, like the universe accidentally invented a laser pointer. And the best guess, the least wrong guess, is that the black hole and its magnetic fields are helping to launch it. How you launch a jet from a black hole is the kind of question that keeps entire careers awake. One idea is the Blandford-Z-Najek mechanism, which sounds like a law firm and behaves like a generator. A spinning black hole drags space-time around with it. That dragging is called frame dragging. And it is not a metaphor. It is literally the geometry of space being twisted by rotation. Thread that region with magnetic field lines anchored in surrounding plasma. And you can extract energy from the spin, not by touching the black hole, you cannot touch it, by using the rotating space-time like a moving conveyor belt for fields and currents. The universe finds ways to do electrical engineering without your permission. But the jet is a side effect, a billboard. The image you want is smaller, quieter, more insulting. You want the shadow, the negative space where light should have been if gravity had not edited it out. To get it, you observe at a wavelength short enough to see fine detail. Around 1.3 millimeters is common for the early campaigns. Shorter wavelength means sharper resolution, but also means more atmospheric trouble. You choose your poison, and then, on the nights when conditions align, the network records. It records with bandwidth wide enough to catch subtle fluctuations. It records polarization too, because polarization holds clues about magnetic fields. And it records timestamps with absurd precision, because time is the needle you will use to sew the planet together. When the observing run ends, nothing feels finished. It feels like you packed a suitcase in the dark, and you will only learn later what you forgot. The telescopes go back to their usual work. People go back to their offices. Someone finally sleeps. But the data does not become an image by itself. Now you enter the part of the story that is even more astronomical than astronomy: the waiting. The data volume is enormous, not because the universe is verbose, but because you are sampling fast and recording wide. You are capturing noise and signal together because you cannot know which is which in real time. So, you keep everything. The result is not a neat folder you can upload. It is a physical pile of hard drives, heavy enough to make your arms regret their life choices. And here is the first mundane cruelty. You cannot just send it over the internet. The bandwidth required would take too long, and too many institutions would start asking questions. So, you do what modern science sometimes does. When it pretends it is not modern, you ship the universe by mail. You remove drive modules from recorders, label them carefully, and put them in protective cases. The cases look like ordinary cargo, which is funny because inside is a synchronized recording of space-time whispering near an event horizon. Congratulations! You are transporting cosmic secrets in something that resembles luggage. From some sites, shipping is easy enough. A truck to an airport, a flight to a correlator facility, a careful handoff. From other sites, shipping is an adventure that feels like it belongs in a less civilized century. The South Pole Station, for example, does not just hand you a parcel and smile. For much of the year, planes cannot land or take off. The darkness and cold lock everything down, so the drives sit there, waiting for the Antarctic summer, when aircraft can return. This means part of your planet-sized eye is forced to keep its memories to itself. For months, it is less like cloud storage and more like burying treasure in ice. Eventually, the drives reach the places that can combine them. The correlation centers. One major correlator is at the Massachusetts Institute of Technology, Haystack Observatory. Another is at the Max Planck Institute for Radio Astronomy in Bonn, Germany. Different centers run parallel processing, both for redundancy and for speed. Now you get to learn what correlation actually means in this context. You take two recordings from two telescopes. They are both streams of sampled voltages, noisy and raw. Each stream is tagged with time from its local atomic clock. In principle, if you align them correctly, the cosmic signal that reached both sites will line up, while the local noise will not. So, you shift one stream relative to the other, searching for the delay that maximizes similarity. You test many delays because you do not know the exact path through the atmosphere, the exact instrumental offsets, the exact geometry at every moment. You are sliding two long, messy tapes against each other, listening for the moment the same melody clicks into place. When it does, you get fringes. Fringes are the telltale interference patterns, the proof that two distant sites heard the same wavefront. It is a quiet triumph, not fireworks, just a line on a plot, rising out of noise like a heartbeat returning. But correlation is not one and done. You do it for every pair of telescopes, for every time interval, for every frequency channel. The network has many baselines, meaning many pairs. Each baseline samples a different spatial frequency of the source, which is a way of saying a different kind of detail. Short baselines capture broad structure. Long baselines capture fine structure. Together, they create a patchy coverage of what mathematicians call the Fourier plane. Fourier space is where images go when they are broken into waves. It is not intuitive, but it is faithful. And interferometry lives there. You do not start with a picture and blur it. You start with scattered measurements of its wave components, and then you reconstruct. It is like trying to rebuild a face from a handful of puzzle pieces, except the pieces are not even shaped like the face. They are shaped like math. So after correlation, you have visibilities. A visibility is a complex number, amplitude and phase, representing how strongly two telescopes agree at a given baseline and time. Complex here does not mean complicated, though it is. It means it has real and imaginary parts, like a signal with both strength and timing. Those visibilities are still not an image. They are the ingredients. And before you cook, you check for spoilage. You flag bad data, a receiver glitch, a snow squall, a pointing error, a clock hiccup, a moment when the atmosphere turned to soup. You remove what you can justify removing, and you document why. Because the easiest way to fake a discovery is to quietly throw out the inconvenient parts. So you become painfully explicit. Every cut is recorded. Every calibration choice is argued over. Every pipeline step is tested on synthetic data where you already know the answer. The goal is not to get a pretty picture. The goal is to get an honest one, even if it looks boring. And this is where the human side becomes almost tender again. Teams across the world are doing the same careful work in different rooms on different computers. Some are experts in atmospheric calibration. Some are experts in receivers and electronics. Some are experts in imaging algorithms. And some are experts in arguing politely, which is an underrated scientific skill. The Event Horizon Telescope collaboration is not one mind. It is many minds attempting to line up like the telescopes did. They have meetings that stretch, they share plots and doubts. They tell each other gently that something looks wrong. They run checks that feel redundant until you remember what is at stake. If you announce a black hole image and later learn it was an artifact, the universe will not forgive you. Not because it cares, because it will keep existing unchanged. while your credibility collapses on a much faster timescale. So, the months pass, the drives are ingested, the correlations are done, the calibrated visibilities settle into databases, and then comes the part that most people imagine as magic, turning signals into a picture. If you are expecting a big red button labeled Render Black Hole, you will be disappointed. What you actually have is incomplete information. No network can sample every baseline orientation and length continuously. Some telescopes are down. Some weather is bad. The Earth blocks some angles, so your Fourier coverage has gaps, and gaps mean ambiguity. Many images could, in principle, match the same sparse measurements. So imaging is not drawing, it is constrained guessing. You choose an image that fits the data and also obeys reasonable assumptions, like positivity, meaning brightness cannot be negative, like smoothness, meaning the image should not invent sharp spikes without evidence. But you must be careful. Too much smoothness can erase real structure. Too little can amplify noise into fake features. Congratulations, you are now negotiating with your own desire for meaning. Historically, radio interferometry used a method called clean. The name is optimistic. Clean assumes the sky can be represented as a collection of point sources. It iteratively subtracts the response of the array to a point, building up a model. Then it restores with a smoothing beam, making something that looks like a picture. For many radio sources, clean works well enough. But for a black hole shadow, for a ring of emission with subtle asymmetry, you want more flexibility. So the collaboration used modern approaches too, like regularized maximum likelihood methods. These methods search for an image that best fits the data while minimizing some penalty term. The penalty is the regularizer, and it encodes your preferences, like smoothness or simplicity. Another approach is Bayesian imaging, where you treat the image as a probability distribution. You ask not just what image is best, but what range of images is plausible. If this sounds abstract, keep it sensory. You are sculpting fog. You have a few flashlight beams shining through it from different angles. You cannot see the sculpture directly. You infer its shape from how the beams dim and scatter. Then you sculpt an object that would produce those beam patterns. And you check, obsessively, that you did not sculpt your own expectations. This is why the collaboration built blind imaging pipelines. Different teams were given the same data, sometimes with hidden modifications, and asked to reconstruct images independently. They were not told what others found. They were not allowed to share intermediate results, because humans are social animals, and social animals copy each other even when they swear they are not. So you isolate the teams like careful gardeners, letting the results grow separately. When those independent reconstructions converge, when they all reveal a ring-like structure with a dark center, you allow yourself a cautious breath. Not relief, not celebration. Just the sense that reality is being consistent. But even then, you test. You generate synthetic data from known models, and you see if your pipelines recover the truth. You scramble phases, you perturb amplitudes, you drop stations, you add noise. You ask, if the shadow were not there, would we invent it? If the ring were different, would we smear it into the one we want? And again, you wait. Because certainty in this business is slow, like paint drying in cold air. At some point, the picture begins to stabilize. It is not crisp like a smartphone photo. It is a blurry ring, thick and uneven, like a glowing donut seen through steam. One side is brighter than the other. That asymmetry is not decoration. It is physics. The gas is orbiting at a significant fraction of light speed. On the side where the flow moves toward you, the emission is Doppler boosted. Doppler boosting is the same family of effect that changes a siren's pitch, but here it changes brightness. Relativistic beaming makes approaching material appear brighter and receding material dimmer. So the ring leans. It has a preferred side, like a face turned slightly toward a lamp. The dark center is not the event horizon itself. It is the shadow, larger than the horizon, because gravity bends photon paths. Some photons that would have reached you are captured. Some are deflected away. The result is a dark depression in the middle, surrounded by light that took complicated routes to find you. In some sense, you are seeing photons that have circled the black hole, not necessarily full loops, but enough curvature to make the geometry feel physical. Light is navigating. Now comes the question you delayed on purpose. How do you know the size of the ring means what you think it means? Because if the ring diameter matches the predictions of general relativity for a black hole of that mass, that matters. Not in a dramatic overthrow physics way. In a quiet, steady confirmation way. You already had mass estimates for the black hole in M87. From the motions of stars, from gas dynamics, from the behavior of the central region, those estimates gave you a mass of several billion suns, with uncertainties, because the universe never signs its work. General relativity predicts a relationship between mass and the angular size of the shadow, given the distance. So you compare. You measure the ring diameter in microarcseconds, a unit so small it feels like a joke. A microarcsecond is like looking at an orange on the moon, which is a tired analogy, but still useful. And the measured size is consistent with a black hole of about the expected mass. Consistent is the word scientists use when they do not want to sound emotional. That word also means you have spent years building a machine just to say, yes, the universe is being itself again. You are allowed a small, private satisfaction. Then you put it back on the shelf because the work is not done. Because a ring is not just a ring. It is a test of a very specific kind of darkness. In a normal photograph, light comes from a surface. Here, the light comes from motion and heat and magnetic violence. The darkness comes from geometry. So you start asking what exactly you have pictured? You have pictured a region where photons are being sorted. Some escape, some are bent, some are simply removed from the conversation. There is a special orbit for light around a black hole called the photon ring. It sounds delicate, like jewelry. It is actually a place where light can circle briefly before being lost or released. In the simplest black hole, the non-spinning kind, that orbit sits at 1.5 times the event horizon radius. In the real universe, black holes spin. Spin drags space-time and shifts these orbits, so the exact structure depends on rotation, viewing angle, and the behavior of the plasma. But the important point is this: the ring you see is not a physical hoop you could touch. It is a brightened pathway, a region where lensing makes more light pile into your line of sight. Your image is a map of how space bends, with a hot, glowing tracer fluid to make the bending visible, which is a wonderfully indirect way to see something. And it fits humanity perfectly, because we are a wonderfully indirect species. You do not conquer the black hole. You triangulate it. You interrogate it through the behavior of nearby matter. You watch it refuse to emit information, and you call that a measurement. Now, the collaboration has a new problem. The world does not want your black hole image to be accurate. It wants it to be a poster. It wants a crisp circle, an obvious monster, a clean lesson, and your actual result looks like a warm bagel seen through a fogged bathroom mirror. So you have to be careful with language and with expectations, because the public thinks image means a single exposure, a shutter click, a captured moment. But your image is a consensus built from many nights, many baselines, and many choices. It is closer to a court verdict than a selfie. And you can tell it is science because nobody is fully happy. Some people want more sharpness. Some people want fewer assumptions. Some people want the ring to be perfectly round because it would feel nicer. And the black hole does not care what would feel nicer. But you can still extract real physics from that blur. The overall size tells you about mass and about whether gravity behaves like the equations say. The asymmetry tells you about orbital speed and viewing geometry. The polarization tells you about magnetic fields and whether they are orderly or tangled. Orderly fields suggest certain jet launching conditions. Tangled fields suggest a different kind of chaos, a disk boiling in its own currents. Even the thickness of the ring tells you about how smeared the emission is, how variable the plasma is, and how limited your resolution remains. And you do not stop with pretty images. You model, you simulate, you build computer universes, little digital accretion flows that obey magnetohydrodynamics, which is the science of moving plasma and magnetic fields. You let them spin. You let them heat. You let them flicker. Then you ray trace them, meaning you compute how photons would travel through that curved space-time toward an observer like you. And you ask a simple question, asked in a very expensive way. Which simulated universe looks most like the one you measured? There is a soft comfort in this loop. Observation to model, model to prediction, prediction back to observation. It is not perfect. It is not clean, but it is a way to keep yourself from telling stories that only sound good. Now imagine the emotional problem buried inside all this careful work. You have made something invisible feel visible, and that changes how your brain behaves. Before, a black hole was math and inference. Now, it is a shape you can recognize. A ring, a void, a crooked smile of hot gas. That recognition is powerful and also dangerous, because once your brain has a shape, it starts believing it understands. So you keep returning to the boring parts, uncertainty bars, calibration errors, station sensitivity, atmospheric phase noise, because humility is not a personality trait in astronomy. It is a survival tool. One of the quietest checks is also one of the most important. You ask whether the image depends on a single telescope. If you remove one station, does the ring persist? If you remove another, does the dark center remain? If you change the weighting of data, does the brightness asymmetry stay in the same place? A real feature should be stubborn. An artifact is usually needy and collapses when you stop feeding it. And then there is another check, even more human. You ask different groups to image the same data using different philosophies. One group prefers smoother images. Another group allows sharper structure. Another group focuses on closure quantities, which are combinations of phases that cancel out some station errors. Closure phase is a small miracle in interferometry. It lets you build robust measurements even when individual telescopes lie a little. You add phases around a triangle of baselines, and many instrumental errors drop out. It is like asking three unreliable witnesses the same question and discovering that their shared contradiction is actually a truth. When those different approaches converge on the same basic ring, you begin to trust it. Not completely. Trust is too emotional. You accept it as the least wrong image consistent with what you heard. And then, at last, you face this simple fact. You have shown humanity the shadow of a black hole. Not by going there, not by sending a probe, but by building an Earth-sized ear and listening very carefully. The announcement in early April of 2019 lands with a strange softness. It is a media storm, yes, but inside the collaboration, it feels like a long exhale, the kind you make after carrying something heavy up many stairs. People show the image at press conferences. They hold it up like a relic. And on the internet, because the internet cannot help itself, it becomes a donut joke, which is perfect. Of course, the first direct glimpse of a black hole becomes a pastry. That is exactly how a species avoids thinking about the abyss, by giving it sprinkles. But while the world laughs and marvels, you keep working, because the first image is not the end of the story. It is a beginning, and it immediately suggests something worse. If you can do this for a black hole in another galaxy, you can try for the one in your own. And that one is closer. Closer means larger on the sky. Larger on the sky means, in principle, easier. In principle is the phrase that always precedes disappointment, because the black hole at the center of the Milky Way does not sit still for portraits. So you pivot slowly towards Sagittarius A star, and before you even try to see it, you have to understand where you are looking. You are inside a spiral galaxy, embedded in its disk, wrapped in dust and gas like a blanket that refuses to be washed. When you look toward the center, you are not looking through empty space. You are looking through layers of ionized gas and turbulent magnetic fields and scattering material that blurs radio waves. In visible light, the galactic center is hidden. In infrared, it begins to peek through. In radio, you can listen more directly, but the scattering still smears the details like frosted glass. And yet, the evidence for Sagittarius A star has been building for decades, not from one dramatic photograph, from patient tracking of stars that orbit an invisible focus. Imagine you are one of those stars. You are deep in the galactic bulge, where star density increases, where gravity is a crowded argument. You swing around a point you cannot see. You accelerate near closest approach, then coast outward, tracing an ellipse. Your orbit is a confession. Astronomers like confessions that repeat. They use infrared telescopes with adaptive optics to sharpen the view through Earth's atmosphere. Adaptive optics is a real-time correction system. A laser creates an artificial star in the sky, a reference point. Sensors measure how the atmosphere distorts that reference. Mirrors flex to cancel the distortion many times per second. It is a way of punching a temporary hole through the atmosphere's bad behavior. With that, astronomers track stars near the galactic center year after year. Some of these stars have names like S2, a label that sounds boring enough to be trustworthy. S2 has an orbital period of about 16 years. It swings close to the center, moving at thousands of kilometers per second near pericenter. It comes within a distance comparable to our solar system scale, which is absurdly close given the mass involved. From that orbit, you can infer the mass at the focus, about 4 million suns, packed into a region so small that no cluster of ordinary stars could hide there without shining. No cluster of neutron stars could remain stable without colliding. No ball of dark objects would survive long without giving itself away. So Sagittarius A star becomes, for most practical minds, a black hole. A quieter one than the monster in M87. But quiet is relative. It still controls the central gravitational landscape of the Milky Way. It still feeds, occasionally. It still flares in infrared and X-rays like a sleeper rolling over. And it is close enough that you can feel emotionally attached to it, which is a mistake. Now you return to the Event Horizon Telescope and the same basic technique. Planet-sized interferometry, millimeter wavelength listening, atomic clocks, hard drives shipped like contraband. But Sagittarius A star introduces a new kind of problem. Time, not your atomic clock time. Source time. M87's black hole is huge. Billions of suns, so the orbital timescales near the horizon are longer. The gas flow changes, but slowly enough that during an observing night, the structure is somewhat stable. Sagittarius A star is smaller, only millions of suns, and that means the dynamical times near the horizon are faster. The gas whips around more quickly. Features evolve in minutes, so you are trying to make a long exposure image of something that behaves like a flickering flame. You can do it, but you have to change your strategy. If you pretend it is static, you smear the ring into nonsense. It is like photographing a campfire with a slow shutter. You will get a soft glow and lose the structure of tongues of flame. So, the imaging becomes a moving target problem. You begin thinking in terms of ensembles and averages. What is the typical structure? What is the persistent geometry beneath the variability? What does the time-averaged shadow look like, even if the surrounding emission dances? You also have to deal with interstellar scattering more seriously. Between you and Sagittarius A star lies turbulent plasma that acts like a distorting lens. It broadens the image and it introduces refractive substructure, little ripples that can masquerade as features. So you must model the scattering and in some sense deblur the universe. This is another case where you do something very human. You take a messy signal and attempt to subtract the mess you did not ask for. You do it carefully, because subtraction is where you can invent things. Now, because this is a bedtime story, let it stay simple. You have a target that is closer but harder. It changes quickly, and the space between you and it blurs it. So you need more data, more nights, more careful algorithms, and more patience. And you need to accept that the final image will not be a single frozen moment. It will be a statistical portrait, the way you might describe a person you see often. Not one expression, but a general face. The collaboration observed Sagittarius A star in the same 2017 campaign that captured M87. But the analysis takes longer, not because people are slow, because the source is mean. They test different approaches, including methods that allow the image to evolve over time. They build libraries of simulated accretion flows, then ask which ones match the measured visibilities. They use closure quantities heavily because those are robust against certain calibration errors. They treat the problem like reconstructing a melody from a noisy room, while the musician keeps improvising. And for years, the public waits. It thinks the delay is drama. It is mostly troubleshooting. It is mostly arguments about whether a feature is real or a product of averaging. The collaboration has learned, painfully, that being first is not worth being wrong. So, when Sagittarius A star is finally released in 2022, it has the familiar shape, a ring, a central dim region, a brightness asymmetry that is less stable because the emission is more variable. It looks like a cousin of M87's image. And that is, quietly, the point. General relativity predicts that black holes of different masses should have shadows with the same basic scale geometry. A 4 million solar mass hole and a 6 billion solar mass hole should both produce a shadow whose size scales with mass, but whose shape is governed by the same space-time rules. So seeing a similar ring around Sagittarius A star is not just a pretty repeat, it is another consistency check in a very different environment, different feeding rate, different variability, different line of sight, through messy Milky Way plasma. And yet, the same basic shadow emerges. You do not prove the theory in one stroke. You accumulate evidence, like sediment, layer by layer, patient and heavy. Now, inside this, there is a more intimate truth. You are living in a galaxy with a black hole at its center. You are not being sucked in. You are not in danger. The central black hole is far, and it is underfed most of the time. It is, compared to active galactic nuclei, practically fasting. The Milky Way is not currently a blazing quasar. It is more like a city after midnight. Lights low, engines idling. Sagittarius A star occasionally flares, likely from blobs of plasma falling inward, or magnetic reconnection events, snapping field lines. Magnetic reconnection is what happens when twisted magnetic field lines break and reconnect, releasing stored energy. It is a common way plasma makes sudden, sharp changes. The sun does it during solar flares. Accretion disks do it too, because nature loves repeating its tricks at different scales. So, your local supermassive black hole is not silent. It is just quiet enough that you can pretend it is not there. But astronomers do not get to pretend. They keep listening. They keep refining, because the first images are a beginning, not a finish. They are like the first time you hear a distant voice clearly enough to recognize words. After that, you want tone and accent and meaning. You want to know how the accretion flow behaves. You want to see how magnetic fields arrange themselves. You want to watch the base of the jet in M87, the place where the outflow is born. And you want, if possible, to test whether the black hole is described by the Kerr metric, the spinning black hole solution in general relativity. Kerr is a name that sounds like a closed door. It is the mathematical description of a rotating black hole, defined by mass and spin, and not much else. No hair, as physicists like to say, meaning no extra features, just those parameters. If you find deviations, it could mean new physics, or it could mean you miscalibrated something, which is why excitement is always tempered by spreadsheets. There is also the matter of polarization, which becomes its own gentle story. Light has orientation. Electric fields oscillate in a direction. When that direction has a preference, we call it polarization. In synchrotron emission, which is common in these plasmas, electrons spiral around magnetic field lines and emit polarized light. So polarization maps become indirect maps of magnetic fields near the event horizon. The Event Horizon Telescope has produced polarized images of M87, showing a pattern that suggests ordered fields near the black hole, ordered enough to support jet launching theories. Not a final answer, but a hint. A hint drawn in faint lines, like chalk on a dark board. And if you keep expanding the array, adding more telescopes, improving bandwidth, you can make the images sharper. You can move toward making movies, not just stills. Because variability is not an obstacle forever. It is also information. The flicker itself tells you about turbulence, orbital motion, and emission regions. So the future of this field is not just clearer pictures, it is time-resolved images, sequences of reconstructions that show the plasma moving, a kind of weather report from the edge of forever. But even here, you keep the tone modest, because this is still earthbound listening. It is still limited by atmosphere, by weather, by funding cycles, by the fact that humans require sleep and food and occasional agreement. The universe is not in a hurry. Your grant deadlines are. Now, speaking of hurry, there is a subtle thing you learn when you look at Sagittarius A star. The black hole shadow size is comparable between the two targets in angular terms. M87 is farther but bigger. Sagittarius A star is nearer but smaller, and yet, from Earth, they both show a shadow around the scale of tens of microarcseconds. That coincidence is part of why these two were chosen. It is also why the story feels like it has symmetry. Two monsters, two rings, two different kinds of patience, and you, in the middle, a species trying to make meaning out of delayed light. Now, let your attention drift back to the practicalities, because the practicalities are where the real story lives. When you image Sagittarius A star, you cannot ignore that the Earth rotates, and your baseline coverage changes. That rotation helps you sample the Fourier plane. But it also means your data is gathered over hours, while the source changes over minutes. So you must reconcile those timescales. You might split the data into shorter segments, reconstruct snapshots, then align and average them. Or you might fit a model that evolves, like a ring with fluctuating brightness patches orbiting. These patches are sometimes called hotspots. A hotspot could be a localized region of higher temperature or density in the accretion flow. If you could track one orbiting, you could test the spacetime more directly. But to track anything orbiting that close, you need a clock you can trust more than your own memory. And you need to remember that a black hole does not give you a clean signal on purpose. The gas is turbulent. The brightness is uneven. The whole scene is a moving argument between gravity and magnetism. So instead of chasing one perfect hotspot, you often settle for something more boring. You look for patterns that repeat. You look for characteristic timescales, the way a mechanic listens for a familiar rattle. Near Sagittarius A star, those timescales are short. A full orbit near the innermost stable circular orbit can be measured in minutes. Minutes is not much time for a planet-sized telescope that gathers data over hours. So, you become a collector of fragments. You accept that any single snapshot is incomplete. You stack many imperfect views, and you ask what survives the stacking. The shadow, if it is real, should be stubborn. The flickering bright knots should smear out like foam dissolving back into the river. This is why the Sagittarius A star image looks familiar, but also softer in its details. It is a time-averaged face, not a candid photograph. Your brain wants to treat that average as a single moment, but the universe is not giving you a moment. It is giving you a personality profile of plasma. And even before the variability, there is the other thief in the room. The space between you and the galactic center is not empty. It is filled with thin ionized gas, and that gas has structure. Not the kind you can see with your eyes, but the kind radio waves feel. Density fluctuations act like a shifting lens, bending and scattering the wavefront. At longer radio wavelengths, the blurring becomes severe. At millimeter wavelengths, it calms down, but it does not disappear. So part of the Sagittarius A star work is learning the shape of the smear. Astronomers characterize it by observing the source at multiple wavelengths. They watch how its apparent size changes with wavelength. They infer the scattering screen, like diagnosing fog, by how it softens distant headlights. Then, in the imaging step, they account for that blur, not by pretending it never happened, by building it into the forward model, the predicted observation for any trial image. This is the theme you keep meeting in interferometry. You do not fix the universe. You model the damage honestly, and you work around it. And because this is millimeter astronomy, the damage includes Earth as well. Water vapor introduces phase delays that can change quickly. So, observatories use tools like water vapor radiometers, instruments that measure the sky brightness from water vapor. That measurement becomes a proxy for how much delay the atmosphere is adding. It is not perfect, but it helps. At some sites, weather is so stable it feels like cheating. At others, the air behaves like it is auditioning for chaos. You compensate with calibration, and with redundancy, and with more observing runs, which brings you to an important detail most people never notice. The first black hole image was not the product of one magical night. The iconic data set came from a coordinated campaign across multiple days, and later improvements come from repeated campaigns across years. Because every extra telescope you add changes the Earth-sized eye. It fills in missing baselines. It sharpens the synthesized beam, the effective point spread function. It reduces ambiguity. So the Event Horizon Telescope is not a fixed machine. It is a growing organism. Stations join. Receivers improve. Recording rates increase. In the earlier days, data rates were already enormous, but the collaboration pushed to higher bandwidth, because bandwidth buys sensitivity. The wider the recorded frequency range, the more signal you can average over. It is like listening with both ears and also borrowing your neighbor's ears. More bandwidth means more hard drives, more shipping, more correlation load. And because science loves trade-offs, it also means more places to make mistakes. A subtle clock error can ruin a baseline. A mislabeled drive can scramble a night. A misconfigured frequency setup can make two stations incompatible. So the collaboration operates with procedures that feel like aviation: checklists, cross-checks, sign-offs. The romance is hidden under paperwork, where it belongs. Now, if you zoom out slightly, you can see why the first images mattered beyond the images. They proved the entire pipeline: the observing logistics, the timekeeping, the shipping, the correlation, the calibration, the imaging, the verification culture, the willingness to distrust yourself. Once that pipeline works, you can point it at other questions. Not just, is there a shadow? But, what is the magnetic field geometry near the horizon? How does the brightness evolve? Where does the jet begin to collimate and accelerate? These are quieter questions, but they are the ones that feed a field. For M87, the jet is the obvious next obsession. You already knew the jet existed. You already had beautiful radio images of it on larger scales. But the base of the jet, the region within a few gravitational radii, is where theories argue. Some models launch jets from the disk. Some launch from the black hole spin, mediated by magnetic fields. In reality, it might be both, because reality rarely chooses one clean mechanism. With the Event Horizon Telescope, you can begin to see structure near the launching region, not as a clean nozzle, more like a bright, compact core with hints of extension. And polarization becomes the flashlight here. When the collaboration released polarized images of M87, the lines were delicate. They traced a pattern around the ring. That pattern suggested magnetic fields that are not purely tangled. There is order in the chaos, at least temporarily. Order matters because jets require collimation. To keep a jet narrow, you need magnetic tension, a kind of field line stiffness. A purely chaotic field struggles to do that. So these polarization maps, even at limited resolution, give weight to certain jet launching pictures. But polarization is tricky. The observed polarization can be rotated by plasma along the line of sight. This is called Faraday rotation. It depends on electron density, magnetic field, and wavelength. At millimeter wavelengths, the rotation is smaller than at longer wavelengths, but it can still matter. So, you measure polarization carefully, and you model how it might be altered. And again, you test multiple pipelines, because polarization is a place where instruments love to lie. Now let your mind drift to what an interferometer actually measures in a more physical sense. Each pair of telescopes measures one Fourier component of the sky brightness. If you had infinite baselines, you could reconstruct the image uniquely, but you do not. You have a sparse set determined by geography and weather and funding. So every image contains an element of inference. This is not a flaw. It is the nature of the method, and astronomers have learned to be honest about it by publishing not just one image, but families of images. They publish error estimates and consistency checks and synthetic reconstructions. They show you what changes when you adjust the assumptions. It is a way of saying, here is what the data really demands, and here is what we gently encouraged. The public often sees only the final ring, but the scientific story lives in the uncertainty, in how robust the ring is against different choices, in how the diameter stays stable, while small-scale brightness patches shift, in how the dark center remains even when you try to talk yourself out of it. And that is where the philosophical part creeps in. Quietly, a black hole image is not a conquest. It is a demonstration of restraint, a global collaboration, agreeing on timing, agreeing on standards, agreeing to let the data contradict their favorite narratives. That is not a natural human behavior. It is trained. It is maintained with meetings and protocols and the shared fear of embarrassment. And it works sometimes long enough to take a picture of darkness. Now, since you are here, let yourself sit with the scale of what you have done. You have used Earth's diameter as an optical element, not by building a lens, but by using separation and time to synthesize one. And it only works because you know where the telescopes are to within centimeters. You know Earth orientation parameters, the slight wobbles and irregularities in rotation. You account for polar motion, the way the crust shifts relative to the rotation axis. You account for tectonic drift because continents are slow but not still. Even the ocean loading matters a little, the way tides flex the ground. This is the level of absurd detail required to say, yes, that bright ring is real. Astronomy looks like stargazing from the outside. From the inside, it is geodesy, meteorology, signal processing, and international shipping, with occasional glimpses of the universe as a reward. Speaking of rewards, one of the strangest outcomes of the first images was how quickly they became familiar. A black hole shadow went from unimaginable to wallpaper. It ended up on mugs, on shirts, on lecture slides used to threaten undergraduates with physics, and your brain, being your brain, adjusted. It stopped feeling like an abyss and started feeling like a logo. So it helps to remember what you are actually looking at. You are looking at light that was heated by friction and magnetic stress in a plasma disk. You are looking at emission produced by electrons moving near light speed, spiraling in magnetic fields. You are looking at radiation that escaped a region where escape is almost impossible. And you are looking at a central darkness that is not a hole in a surface. It is a region of space-time where outward paths do not lead outward. That is what the image means under the cozy blur. Now, there is another layer of subtlety in these images that is easy to miss. The ring you see is not necessarily the same as the thin photon ring predicted in idealized textbooks. The photon ring is a very narrow feature, produced by photons that orbit one or more times before escaping. In practice, current images are dominated by emission from the accretion flow, lensed into a ring-like shape. The photon ring may be present but unresolved, buried inside the broader emission. Future arrays with more stations and higher frequencies might isolate it. That would be a sharper test of general relativity because the photon ring geometry is more universal. The messy plasma emission depends on astrophysics. The photon ring depends more directly on space-time. So, the collaboration talks about upgrades, more telescopes, better receivers, higher data rates, maybe even space-based stations to extend baselines beyond Earth's diameter. Because Earth-sized is impressive, but it is also a ceiling. If you want sharper than Earth, you leave Earth. And that is a different kind of logistics nightmare with a different price tag. But astronomers think about it anyway, because thinking is cheaper than building. Now, let the story return to Sagittarius A star for a moment, because it has its own quiet lessons. Sagittarius A star is underfed compared to active galactic nuclei. Its accretion rate is low. That means the disk is not a classic bright, thin disk like in some quasars. It is more like a hot, puffy, radiatively inefficient flow. Radiatively inefficient means the gas does not turn much of its energy into light before falling inward. It stays hot, but dim, because the plasma is tenuous and collisions are rare. Energy can be carried inward rather than radiated away. So Sagittarius A star is a black hole with a small appetite and a messy kitchen. This affects what you see at different wavelengths. At radio and millimeter, you see emission from close in. At infrared, you see flares that may be tied to magnetic reconnection and transient heating. At X-rays, you see occasional bursts, but the overall output is low. Low output is good for your bedtime, because it means the galactic center is not currently sterilizing the inner galaxy. It did not always have to be this quiet. There is evidence in structures like the Fermi bubbles that the Milky Way center may have been more active in the past. The Fermi bubbles are large lobes of gamma-ray emission extending above and below the galactic plane. Their origin is debated because the universe enjoys debate. They could be from past outbursts of Sagittarius A star or from star formation-driven winds in the central region. Either way, they remind you that quiet does not mean gentle. Quiet can be temporary. Now, if you step away from the black hole itself, the Event Horizon Telescope story also touches something more general. What does it mean to make an image in science at all? A microscope image is often processed. A medical scan is reconstructed from projections. A gravitational wave signal is extracted from noise with matched filtering. Modern science frequently operates in a world where raw reality is inaccessible. You measure an imprint and you reconstruct a model that best explains it. And the black hole image is one of the most famous examples of that reconstruction culture. It teaches the public, if the public is willing, that seeing is not always direct. Sometimes, seeing is inference done with care. Now, because you are the kind of person who listens to sleepy science about black holes, you might appreciate one more slow, technical detail. The Event Horizon Telescope does not measure absolute phase easily. Atmospheric fluctuations scramble phase at each station, but closure phase, formed by summing phases around a triangle of baselines, cancels station-based errors. Closure amplitude, formed from ratios of amplitudes around a quadrangle, can also reduce calibration dependence. These closure quantities are why the method works at all in such hostile conditions. They are invariant under certain kinds of corruption. So a lot of imaging work relies heavily on closure phases because they hold onto geometry even when the atmosphere misbehaves. It is like building a map using only the angles and triangles, even if your ruler keeps changing length. And that trick, invented decades ago for radio astronomy, became essential for imaging a black hole. Old math, new target, a recurring theme, because the universe does not update its software. Now, while the Event Horizon Telescope was doing all this, there was another quiet revolution happening in parallel. Computing improved. Storage improved. Not in a single dramatic leap, but in the slow accumulation of better tools. You can run magnetohydrodynamic simulations with higher resolution than earlier generations could afford. You can ray trace photons through curved spacetime with more realism. You can test imaging methods on thousands of synthetic data sets. This matters because black holes are not only hard to observe, they are hard to interpret. If you see a bright crescent, is it Doppler boosting, lensing, optical depth effects, or all of the above? If polarization is ordered, does that mean the magnetic field is ordered? Or does it mean the emission region selects for a coherent component? Interpretation requires models that are at least not ridiculous. So computational astrophysics becomes the other half of the telescope. One half listens, the other half imagines, and then they argue until they agree, or until the paper deadline arrives. Now, speaking of paper deadlines, there is a gentle human truth inside large collaborations. Credit is complicated. Authorship lists are long. Decisions are slow. You cannot simply have one person declare victory. So collaborations develop governance, working groups, internal review committees, publication boards. It is not romantic, but it is how you prevent a single enthusiastic person from sprinting off a cliff with the group's reputation. And this, too, is part of the black hole image story. Not just physics. Social engineering. Humans building structures that allow them to cooperate at planetary scale without dissolving into chaos. Sometimes the structures even work. Now, with two shadow images in hand, one from M87 and one from Sagittarius, astronomers begin to do comparative black hole astronomy. Not just, here is a black hole, but here are two black holes with different masses and environments. M87 is in a massive elliptical galaxy with a strong jet and higher accretion activity. Sagittarius A* is in a spiral galaxy with low luminosity and intermittent flares. Their shadows are similar in scaled shape, as expected, but their surrounding emission differs because feeding matters, and that difference becomes a tool. You can ask how accretion behaves across regimes, how magnetization changes, how jet launching depends on spin and magnetic flux. Some models talk about magnetically arrested disks, where magnetic fields become so strong they partially choke accretion. In that regime, magnetic flux piles up near the black hole, and jet power can increase. The phrase magnetically arrested disk sounds like an overreaction, but it is descriptive. Fields can indeed become dominant enough to arrest inflow intermittently. Whether M87 is in that regime is an active question, because active questions are the oxygen of a field. Sagittarius A* might be in a different regime, less magnetically choked, more tenuous, more chaotic. So the same imaging machinery becomes a way to compare plasma physics in extreme gravity. Now, let the scope widen a little, because the outline wants the story to become less about a single triumph and more about what it changed. The first black hole image did not suddenly make black holes real. Black holes were already painfully real in the math and the evidence. The image gave your visual brain a handle. It let non-specialists feel the geometry, and it gave astronomers a new kind of data. Data on horizon scale structure. Before, many measurements were indirect. Stellar orbits, gas dynamics, variability power spectra. Now, you have spatially resolved information at the scale of the event horizon. That is a new regime. It is like going from hearing thunder to seeing the lightning channel. Not perfectly sharply, but enough to say, yes, that is the shape of the strike. And with that new regime comes a quiet shift in what questions feel reasonable. You begin to ask about deviations from the Kerr metric, about alternative compact objects like boson stars or gravastars, theoretical constructs that mimic black holes in some ways. Many alternatives are constrained by the shadow size and shape, because if you had a surface instead of a horizon, you might expect different emission signatures. Not necessarily in a simple way, because astrophysics can hide things, but the parameter space shrinks. So the image becomes one more boundary stone on the map of possible realities. It does not tell you everything. It tells you some things are less likely. Science often advances by pruning. Now, there is another quiet effect of these images. They force you to confront the meaning of resolution in a deep way. When you say you resolved a black hole shadow, you are really saying you had enough baseline length and enough signal to detect structure at that angular scale. But the image is still limited by sparse sampling. Sparse sampling means your planet-sized eye is not a perfect circle. It is more like a handful of long threads stretched across a dark room. Each thread measures one kind of detail at one angle for a short time. You can feel the missing information, like gaps between fence boards. So resolution is not a single number that guarantees truth. It is a promise with fine print, written in weather and geography. You can say you can, in principle, see a micro-arcsecond feature, but only if your baselines actually cover the right directions. Only if the signal survives the atmosphere with its dignity intact. Only if your calibration does not quietly tilt the playing field. And that changes how you think about an image. An image becomes less like a window and more like a negotiation. You take incomplete measurements and you ask for the simplest sky that fits. Then you ask again with different assumptions to see what breaks. The features that stay put are the ones you keep. The features that vanish are the ones you politely forget. That is not cheating. That is how you keep your imagination on a leash. Now the discovery quietly changes something else too. It changes who astronomy belongs to, at least for a moment. The old myth is a lone observer at a telescope, a single figure in a dome, whispering to the stars. That still happens sometimes in quieter projects. But an Earth-sized interferometer does not tolerate romance. It needs operators in different time zones doing boring tasks correctly. It needs engineers who understand cryogenic receivers and vacuum pumps. It needs programmers who do not panic when the data is ugly. It needs technicians swapping hard drives at 3 in the morning. And it needs administrators, the unseen gravitational field, scheduling flights and shipments. The first black hole image looks like a triumph of physics, it is also a triumph of people agreeing to be careful together, which is, frankly, rarer than a supermassive black hole. And in the middle of that cooperation is a kind of modesty. No single telescope can claim it did the job. No single country can claim it owns the shadow. The image is a stitched artifact built from separate nights and separate hands. If you want a symbol for science that is not a lone genius, this is it. 1,000 small competencies aligned long enough to hear a whisper. Of course, the universe immediately punishes you for feeling proud. Because a picture is not a full understanding, a ring does not tell you the exact spin cleanly by itself. A crescent does not hand you the magnetic field strength in plain language. The image is a beginning of constraints, not the end of questions. So you do what astronomers always do after a famous result. You return to the machinery and you ask what else it can say. For M87, you stare at the jet again. You remember that the jet is not just a pretty line. It is a way the black hole edits the galaxy around it. Jets can heat gas in galaxy clusters, preventing it from cooling and forming stars. They can inflate bubbles in the surrounding plasma, like slow cosmic bruises. They can regulate growth, a feedback loop with no emotions. If you are a galaxy, a jet is a lifestyle choice forced on you, and the black hole, invisible and compact, sits at the center like a silent manager. So the black hole image becomes part of a bigger story, not just what is a black hole, but how do black holes sculpt the universe on large scales? It is one of the cruel jokes of cosmology. The smallest regions can control the largest structures. A horizon-scale engine can influence a cluster-scale atmosphere. And humans who struggle to manage a small town are trying to model this. You can see why they look tired. Now, shift your attention to something even quieter. The image also changes the culture of testing gravity. General relativity has been tested many ways, many times. Mercury's orbit, gravitational lensing, time dilation, pulsars, gravitational waves, but those tests often probe weak fields or dynamic mergers. A black hole shadow probes strong field gravity in a steady state. It is a different corner of the theory. Not a new theory, but a new place to look for cracks. The EHT result does not show a crack. It shows that the wall is still standing. And that is valuable, even if it is boring. Because boring in physics is another word for consistent. The size of the shadow matches the expectation for a Kerr black hole. The ring is roughly circular, within uncertainties, as expected. If it had been wildly distorted, people would have screamed. Instead, they nodded and wrote careful papers and argued about systematics. That is how you know it is real science. Excitement is brief. Error budgets are forever. And since you now live in a world where black holes have images, you start noticing the next steps. You start hearing people talk about higher frequencies. 230 gigahertz becomes a familiar sound. Then you hear about 345 gigahertz. Shorter wavelength, sharper view, less scattering. Also, more atmospheric pain because water vapor never stops being petty. At higher frequencies, fewer sites have good weather simultaneously. So you want higher, drier places. and better receivers. You want more sensitivity so you can work faster before the atmosphere decorrelates phases. You want better clocks, better calibration, better everything. And you want more stations, because empty gaps in the Fourier plane are where ambiguity breeds. Add a telescope in a new location, and you draw new lines across the invisible math. You turn the fence boards into a tighter lattice. You reduce the range of possible skies that match the data. This is why the EHT keeps expanding. It is not just a one-time stunt. It is an evolving instrument assembled from geography and persistence. Sometimes people talk about the next generation EHT. More bandwidth, more sensitivity, more sights, faster cadence. And the dream, always hovering, is movies, not a single ring, but a ring changing in time. Not just a portrait, but a living scene of plasma orbiting and flaring. For Sagittarius A-star, a movie is not a luxury. It is the correct format for a restless source. You do not photograph a flame once and declare you understand fire. You watch the flame move and you learn its habits. And yes, it is still strange to call this watching, because you are watching through layers of inference. But if the inference is stable and the checks are ruthless, it counts. Now, let the story widen gently into the quieter consequences. The first black hole image becomes a lesson in what modern observation really is, because a surprising amount of modern science is built from reconstruction. In medicine, a CT scan is not a direct photo. It is a computed map built from many X-ray projections. In seismology, you infer Earth's interior from waves you never see directly. In particle physics, you infer invisible particles from missing energy in tracks. In gravitational wave astronomy, you dig a faint chirp out of noise, using templates, so the black hole image fits into a larger human pattern. You do not get reality raw. You get reality filtered, sampled, and partially corrupted. Then you build the best story that explains the evidence. The difference between science and fantasy is that science keeps the receipts. Calibration files, uncertainty estimates, blind analyses, cross-checks. The boring paperwork is the wall between you and self-deception. Now consider the emotional side, the part people rarely say aloud. A black hole image does something to your sense of scale. You are lying in bed in a room small enough to cross in a few steps, and yet you can hold in your mind a ring of light around a hole in space-time. That ring is made by plasma moving near light speed around an object whose mass can outweigh entire star populations, and you can hold it as a picture like any other picture. That should feel empowering. It should also feel absurd, because the universe did not get smaller. Your symbols just got better. Your species is good at turning terror into an icon, a donut, a logo, a wallpaper, the abyss made printable. But the underlying thing remains what it is, a one-way boundary where information stops escaping, a region where your usual instincts about space do not apply. And this leads to a calm, grim thought. The universe is not obliged to be intuitive. It simply happens to be mathematically describable, which is a strange kind of mercy. Now, since you have been patient through all this, you deserve a small, grounded detail. The famous image of M87 is often described as the first image of a black hole. Strictly, it is the first horizon-scale image of a black hole shadow. That sounds picky because it is. Astronomers have imaged black hole environments before, just not at this scale. They have seen accretion disks in X-rays, indirectly. They have mapped jets on larger scales for decades. They have tracked stars orbiting Sagittarius A star with exquisite precision. But the shadow itself, the central depression shaped by photon capture, was new. It was the first time the geometry had a face. And faces matter to humans. We are pattern recognition machines that panic without a shape to hold. So, the EHT gave the public a shape, and it gave researchers a new observable. Shadow diameter, ring asymmetry, polarization structure. These become new ways to test models. Not perfect tests, because the plasma physics is messy. But they are additional anchors. More anchors means fewer ways for your theories to float away. Now, follow one more quiet thread. The EHT story also shows you the limits of what you can claim from a single image. If you see a ring, you cannot immediately read off spin like a speedometer. Spin affects the shadow shape a little, but not dramatically for many viewing angles. The shadow remains close to circular and Kerr geometry for moderate spins. The main changes are subtle distortions and shifts. Those subtle changes are hard to isolate when your coverage is sparse. So, when you hear people say, "We measured the spin from the image," you should blink slowly. You can constrain spin with additional information, like dynamics, jet orientation, polarization, variability. But the image alone mostly confirms the existence of a compact object with a shadow of the right size. That is already impressive, and also already limited. It is a reminder that nature does not hand you clean parameter readouts. You must coax them out with multiple lines of evidence. Now, speaking of multiple lines of evidence, the shadow images link nicely to something else that happened in the same era. Gravitational wave detections. Those chirps from merging black holes are another way of making the invisible visible. They do not give you a picture, they give you a waveform. But both methods share a theme. You infer black holes not by seeing a surface, but by seeing effects, space-time ringing after a merger, light bending into a ring around a shadow, different messengers, same refusal of direct contact. Black holes stay shy, and you stay stubborn. And since you are a time traveler in spirit tonight, you can appreciate how these methods would sound to earlier astronomers. Tell someone in the 19th century that you will image a black hole by synchronizing clocks on mountaintops and shipping hard drives. They would assume you are ill. Tell someone in the early 20th century that you will detect black holes by measuring space-time ripples with lasers. They would assume you are writing fiction. And yet, here you are, in a world where both happened. Not because humans became wise, because humans became organized and built instruments and tolerated boredom. Now the story turns gently toward what this discovery changed in the night-to-night practice of astronomy. It made calibration culture more visible. It made the public aware that most of science is not the moment of discovery. Most of it is the slow refusal to be fooled. The EHT had to be careful in a way that resembles forensic work. What did the instrument actually measure? What could corrupt it? What assumptions did the imaging impose? How robust are the results to missing stations and altered weights. This becomes a template for future, large collaborations. It is not glamorous, but it is transferable. And it also changed what students think astronomy is. Not just looking through a telescope, but writing code, processing signals, managing large data sets. It is a reminder that astronomy is now partly a computer science field. The sky is still above you, indifferent and quiet, but the path from sky to knowledge runs through servers and algorithms. A modern observatory is half dish, half data center, and the people who keep it running are often invisible too, which is fitting for a project about imaging darkness. Now, let yourself drift outward again, into the bigger cosmic implications. Black holes are not just endpoints of stars. Supermassive black holes seem to sit in the centers of most large galaxies. They are like seeds or like nuts, depending on your mood. There is a relationship between black hole mass and the properties of the host galaxy. The bulge velocity dispersion correlation is one famous example. It suggests co-evolution, a long negotiation between galaxy growth and black hole feeding. The jet and radiation output can heat gas and suppress star formation. Meanwhile, galaxy mergers can feed the central black hole and make it grow. So, black holes are not simply cosmic trash cans. They are active participants in galaxy life, even if they do not shine directly. When you image M87's black hole, you are not just seeing a distant object. You are seeing a node in a much larger ecological network, a galaxy cluster ecosystem, where hot gas fills space between galaxies, where jets can inflate cavities in that gas, where cooling flows can feed central regions. The black hole sits at the center of that, like a thermostat without compassion. And that too is cozy cosmic horror, a hidden object that regulates the fate of billions of stars, not by intention, but by physics. Now, if you zoom even farther out, you can hold a gentle paradox. Black holes are where information seems to disappear, at least classically, and yet they are central to the way the universe organizes matter. They are both sinks and engines. They are dead ends for light and launchers of jets. They are simple in the equations, described by mass and spin and charge. And they are complicated in practice, surrounded by plasma turbulence and magnetic fields. The EHT image sits at that boundary. It is an observation of something theoretically simple, wrapped in something physically messy. The shadow is geometry. The glow is astrophysics. And your job, as the sleepy observer, is to keep those distinct in your mind, because the temptation is to treat the whole picture as pure relativity. In reality, much of what you see is the behavior of hot gas. Relativity shapes the pathways. Plasma physics supplies the paint. Now, for a moment, imagine you are one of those photons in the ring. You are born in a chaotic region of plasma. An electron spirals in a magnetic field, emitting synchrotron radiation. You are that radiation, a millimeter wave with a long, lazy oscillation. You leave the plasma and immediately face curved spacetime. Your path bends, not because you feel a force, but because the map is warped. You swing around, maybe once, maybe not. You pass through more plasma that can absorb or scatter you. Then you escape outward, and the environment becomes emptier. You travel for millions of years, indifferent to the meaning humans will assign. You pass through intergalactic medium, thin as a thought. You pass by stars that never notice you. Finally, you reach Earth. You hit the atmosphere and pick up a little delay, a little phase noise. You arrive at a dish in Chile and also at a dish in Hawaii, separated by an ocean but linked by time tags. And then you become data, voltage samples on a hard drive, shipped in a case. Later, you are correlated, aligned with your sibling photon samples, and you contribute infinitesimally to a ring in an image. Congratulations, you traveled across the universe to become a pixel in a donut. It is not the destiny you imagined, but photons do not imagine. Now, take that same sympathy and apply it to the humans. The people on those mountaintops are also running on small supplies. Oxygen is thin, sleep is broken, coffee is strong. They do not feel cosmic. They feel cold and tired and careful. They worry about receiver noise temperatures and pointing models. They worry about a cable that looks worn. They worry about the clock staying locked. And yet, their small worries add up to a world-changing measurement. Not because the universe cares, because humans care and can sometimes synchronize their care. Now the outline wants the story to broaden into a calm reflection. Not a conclusion, just a widening of the frame. The black hole image did not end the mystery. It made the mystery more precise. You now know what questions to ask with sharper language. How thick is the emission region? How does polarization evolve in time? What is the electron temperature distribution? How does the magnetic flux accumulate near the horizon? Do the images match magnetically arrested disk models? Does the jet power imply high spin? Is there evidence of non-Kerr structure? Even subtly. And those questions, while technical, have a very human center. They are about limits. What happens when gravity is strong enough to trap light? What happens when matter is hot enough to become plasma and organize itself with fields? What happens when time runs differently near a horizon? And what happens when a species with soft bodies tries to understand it from far away? The answer is always the same. You build instruments, and you wait, and you check your work. You do not get certainty. You get convergence. Multiple methods pointing to the same shape. Multiple teams agreeing on the same ring. Multiple years reproducing the result. It is slow, and it is almost boring, and it is therefore trustworthy. Now, you can let your thoughts wander to the night sky again, not in a poetic way, but in a practical way. Every bright star you see is a nearby success story of fusion. Every dark patch is dust, not emptiness. Every faint smear is a galaxy with its own central gravity problem. And in many of those galaxies, a black hole sits quietly in the middle, not as a monster waiting to jump out, as a natural consequence of matter having gravity and time being finite. Stars die, galaxies merge, gas falls inward. Over billions